Okay, well, good afternoon. Welcome everyone to the Arena Insights Green Steel webinar. My name is Lisa. I am part of Arena's knowledge sharing team, and I will facilitate today's session. So looking at people joining in, that's great to see so much interest in this space. I'm sure people are kind of dialing in from different Indigenous lands around Australia. Therefore, I would like to begin by acknowledging the traditional custodians of country throughout Australia and pay my respect to elders past and present. I would also like to extend that respect to all Aboriginal and Torres Strait Islander people that might be attending the session today. So just a couple of logistic notes before we actually dive into the program. First of all, the event is being recorded and the recording will be posted on our Knowledge Bank on Arena website in the coming weeks. So you'll be able to go back and watch, your favorite presentation if you like. We will have two Q&A sessions. One will be halfway and the other one at the end of the meeting. And we would really encourage everyone to have a good interactive discussion. So if you have a question, please just feel free to raise your hand, your little hand at the top of your team window. I guess we are now used to that, hopefully. But if you raise your hand, I can allow you to come off mute and ask your question. If you prefer typing your question, that's also fine. You can use the Q&A function and try to address these questions. So, why are we all here today? Well, unfortunately, I am definitely not expecting to reach net zero by the end of today's webinar. But I think really that kind of sharing knowledge on the potential pathways to decarbonize a really massive emission-intensive sector like the steel industry is really a good way to kind of accelerate the transition. So in particular today, we'll hear about the key results from the studies and pilots undertaken by BlueScope and Calix. We'll get some insights from the Mineral Research Institute of Western Australia, in particular on the emission reduction opportunities, as well as the economics of different green steel technologies. And finally, we'll provide a brief snapshot of the iron and steel R&D projects that are currently supported by Arena. So to kick off really the presentations, I would like to introduce the BlueScope team. We've got Andrew McClure, who is the Government and Regulatory Project Manager, and Ian McDonald, who is the Manager of the Carbon Abatement. And they are going to talk about the outcomes of their Port Kembla emission reduction study. So over to you, Andrew.
Thanks, Lisa, and welcome everybody. So I suppose we'll just talk about, mainly this is about the Port Kembla Steelworks and the work that we're doing around our steelworks to reduce our emissions. If you just keep going, please. Won't hesitate on this, just keep going, please. But yeah, just a note for people to understand. Today's agenda, we'll break it into 3 seconds, just a very quick introduction. We'll talk about the study that we did supported by Arena with the University of Wollongong. And also Ian's going to talk about some of the work we're doing around the long-term future. Thanks. Just introduction, yep. So I suppose what we're really talking about is around an integrated steelworks. So Port Kembla is known as integrated because we import raw materials like iron ore and coal and limestone, and we use those raw materials to first produce iron and then to convert that into steel and then cast it and then roll it. But of course, the iron making aspect is really the thing that we want to talk about, because that's where the source of the emissions are, because within iron making, of course, we're using coke and coal to reduce the iron ore to iron. Next, please. So this slide is showing BlueScope's indicative decarbonisation pathway. And so it's really into two areas. So we're looking at the first area, which is out to 2030 plus, is continuing blast furnace operations and what we might do in that area. And then post that is looking at the future technology pathways. And so we know that the blast furnace is very mature and a lot of work has gone into getting the efficiency of the furnace working very well, but we will still work on improving the efficiencies, and there's a few things there around process efficiency, using renewables where we can, and also for us it's about increasing the amount of scrap we use, which will improve our or reduce our intensity. And then long term, and Ian's going to talk a bit about the long term today, looking at direct used iron, and then maybe some of the other things as well, but also the enablers that can help us to get to that future technology pathway. Next, please. Yeah, so now I'm going to talk about the project that we did and with ARENA support to look at what things we could do on our decarbonisation pathway. Next, please. And really, this is a very quick look at this project. As I've mentioned, BlueScope was working with the University of Wollongong very closely and also had input from the Future Fuels CRC. And we were looking at sort of how do we support our targets and goals, looking at the potential short to medium and then the long-term decarbonisation pathways. And part of those were smart carbon usage and direct carbon avoidance as typical ways at which we could reduce our emissions. And also a big part of the project was some laboratory and plant biochar trials, and I suppose that's along the lines of using the renewables. Thank you. So this slide's really busy and not going to go into any detail, but as part of the project, and really this part of the project was done by the university, and they did a great job of looking up at all the different technologies that you could potentially use to reduce emissions within an integrated steelworks and also into the future. So this gave us a really great starting point to look at what was out there and then work on what might work for Port Kembla Steelworks. Next, please. So, of course, you know, we had over 100 different technologies to look at, and we worked to reduce that fairly quickly. So we looked at the short term in the sort of 15-year time frame, and because of that sort of time frame, we were able to say, look, if something's got a really low TRL, then it probably means that it's going to take 5, maybe 10 years to get going. And that really would impact its ability to help us in that short to medium term. And then likewise, in the long term, we were really looking for technologies that would significantly reduce our emissions. And that sort of helped us reduce the options that we needed to assess further. And I think we got down to about 20 technologies that we then moved into doing detailed assessments on. And as you see there, we looked at a number of like the detail of each of those, but also looked at the operations, engineering, safety and environment aspects as well. And that helped us to look at what we might do going forward at Port Kembla. Also, as part of the detailed assessment, we did some work on looking at a simulation model, and we looked at some options around hydrogen, coke ovens gas injection, and different types of biomass. So we looked at biochar and also at a torrefied charcoal type process, just to look at how those injectants into the blast furnace would work, what the emission levels might be, what levels we could actually inject into the furnace, those sorts of things. Okay, next please. So out of that work, we've really identified a few items to look at, understanding that we don't have unlimited resources. And I suppose the three short to medium term ones are looking at potential to use HBI, hot briquetted iron, in the blast furnace. And we've picked that up from the likes of Kobe Steel, who have done work on using that and an overall emission reduction for the blast furnace or for the operation. We've looked at biomass and particularly biochar, and I've got a slide on that next. And also we wish to look at more scrap utilisation in our operations, particularly in the BIF. And we've done a lot of work in that area already, but we see there's still more opportunities to do in that area. In the long term, we really are focused predominantly on the direct reduction of iron, and Ian will talk a little bit about that. Okay, next please. So as I mentioned, one of the focus areas for the study was around biochar use, and as a replacement for the pulverised coal we use in the blast furnace. So a very quick explanation. We use coke and we use coal in the blast furnace. So the coke is fed in through the top, and the coke's a very important part of the iron making process, and helps, I suppose, the blast furnace breathe as the material works its way from the top of the furnace down to the bottom, and also provides the reductant and the energy within the blast furnace. But more recently, we have been able to use coal and inject that into the base of the blast furnace, and that has been very effective in, again, adding energy, but also as a reductant. So the idea of the biochar work was to pick up on the previous work that we had done with World Steel CO2 Breakthrough Program, which really identified that biochar could work, particularly in PCI, but other areas, but we focused on PCI. And so part of this project, and with Arena's support, we procured 1,000 tonnes of biochar, and that was quite difficult. There's a limited amount of biochar, and there's certainly not a bulk supply of biochar in Australia, but we got 1,000 tonnes. First of all, we conducted tests at the university. So we were looking at I suppose, the properties of a mix of biochar with the PCI coal. And then also we did trials, and the Bulk Materials Engineering Australia at the university actually have, and you can see the picture there, but they have a test rig, which is for pneumatic conveying of materials. And so that provided a really good way of checking how a mix of biochar and PCI coal would go together. And all of that work indicated that we should not really have a lot of problems using the biochar mixed with the PCI coal within the furnace. And then we conducted plant trials. So most of that 1,000 tonnes was mixed in different areas, different ratios with the PCI coal, starting off at 5% and ending up at 30%. And so our PCI plant works along the lines of, it's got bins. We heat the coal and we grind it, so we get rid of the moisture and we get the right size for feeding it into the furnace, and then we pneumatically convey it into the furnace and into the tuya level of the blast furnace. And so through those trials, we would say that they were very successful, still being a low quantity. So you know, the maximum we had was 30% of the PCI coal being biochar, and that was for a 24-hour period. So still limited, but giving us a good indication that it's something that we could do in the future. And of course, the other side of it was looking at the performance of the blast furnace at that time, and we didn't see any negative impacts of the trials. So certainly biochar is something that we continue to look at, and Ian's very much involved in doing that. So that's the biochar side of things. Next, please. So Ian's now going to talk about some of the future work that we are doing, and looking at that long-term decarbonisation pathway.
Thanks, Andy. Yep. Yeah, so I thought I'd just start quite quickly with the background of some of the different steelmaking technologies. I hope this is of interest to most people. Yeah, so there's really three main routes, and the dominant route worldwide is the blast furnace or integrated steel making route. So that's approximately 70% of steel is made with that route. The other primary steelmaking technology that's a focus is the electric arc furnace, where scrap is reheated to make steel. That's often called secondary steelmaking. So that's 23%. And the third option is direct reduced iron, and that's what a lot of people are interested in at the moment, especially with using hydrogen. So DRI is used pretty much where natural gas is cheap at the moment, which is in the Middle East and in America, North America. This ratio is very dependent on geography, I guess. So in the US, it's about 70% EAFs, and in China, it's about 90% blast furnaces, because that's due to the maturity of the country's industry, I guess. So there's more scrap availability in the US. Next slide, please. So this is a look at the different types of technologies. So Port Kembla Steelworks is the one on the left. It's a typical, we use hematite, iron ore, coal, and I've got a blast furnace, and then we've got a BOF. It's a mature technology with a greenhouse gas intensity of about 2. The other one that's mature is an electric arc furnace, which depends on the electricity greenhouse gas intensity. So depending on the amount of renewables in the grid, but yeah, it's quite a lot less, from about 1/3 to 1/4 of the greenhouse gas intensity. And I guess one of the big questions that everyone asks is, why don't we at Port Kembla switch to an electric arc furnace? And the simple answer is, we don't have enough scrap. We currently do import some scrap even now. Yeah, but looking forward, there's two different options. I guess the most common one is the one on the right, which is DRI straight to an EAF. That needs magnetite, which is a little bit more expensive and less common. And the option that we're pursuing in a partnership with Rio Tinto and BHP is a DRI, an electric smelting furnace, and a BOF. And the two advantages of that option are cheaper raw materials, and secondly, utilising existing infrastructure. So yeah, we already have a BOF. Next, please. Yeah, just to highlight this situation, the world needs primary steel, and it's going to be more and more steel needed over time. So there is a gap between the amount of scrap and the amount of steel we require. So yeah, if someone converts to an EAF, someone else will have to produce more primary steel. So next. Yeah, so it's been announced fairly recently. So we're working with Rio Tinto and BHP to produce a electric smelting furnace, ESF. So that the whole idea of that is to trial a Pilbara ores, using hematite Pilbara ores, to make in an ESF, which hasn't been done before, and it is really essential going forward. So we're working very early days, but we're working through that at the moment. Next, please. I think this is the last slide, and it is a little bit controversial, but the reality is that natural gas DRI is a huge step down from a blast furnace BOF process. Hydrogen may well be the final step, but we don't really want the perfect to be the enemy of the good, so to speak. So you can get a 50 to 60% reduction, direct reduction from a blast furnace to a natural gas DRI. So that's the sort of focus for us at the moment. Yeah, and it's been talked about before, but for steelmaking, it definitely is a transition fuel. So it's something we really need to work for, which is natural gas availability. Yep, that's it, I think. Oh, sorry, that made it to the end. Yeah, so I have been working on biochar. It's part of probably half my role at the moment is trying to work out a source of biochar. It's a really easy option for us in that we don't have to reconfigure the existing steelmaking process. Yeah, the trial was very successful, as Andy mentioned. We had a 30% blend for 24 hours. That's not to say we can use it every day of the week, but it's certainly a very good thing. And it does make a significant reduction in our greenhouse gas emissions. Yeah, so I guess at the moment there's no supply chain, as Andy mentioned, but yeah, we're working with several partners to try and make that happen. Thanks.
All right, thank you so much, Andrew and Ian. Really nice presentation, and great also to see how you kind of refine your strategy based on the study outcomes. So now I would like to hand it over to Chris Ormston, the general manager at Calix, who is going to talk about the results from their FEED study. So over to you, Chris.
Thanks, Lisa, and hello, everyone. My name's Chris, and I'm the General Manager at Calix for Sustainable Processing, and I'm delighted to present to you today the FEED study outcomes of a hydrogen direct reduced iron demonstration plant, which has been kindly supported by ARENA. Next slide, please. I'll allow you to read the important disclaimer notes at your leisure for a few minutes. Next slide, please. So at Calix, we're a dedicated team of industrial research, engineering, and technology professionals dedicated to saving urgent global challenges in industrial decarbonisation and ensuring a sustainable future for minerals and metals processing. We were founded in 2005 and listed on the ASX in 2018, and we currently have over 120 employees spanning across 7 countries and 5 continents. We've invested over $120 million in the development of our platform technology to date and own 28 patent families. Next slide, please. So our platform technology is simply described as a new way to heat stuff up. So the process vessel, or a calciner tube, as you can see on the left there, is directly heated using fuel or electricity and is also renewable energy ready. You can see the picture to the right. Our facility here in Bacchus Marsh in Victoria is equipped with solar panels with sufficient capacity to fully power the pilot plant on renewables. In the process, pre-ground minerals are introduced to the top of the calciner and float down through the tube, enabling the thermal reaction to take place. High purity or converted materials exit the base of the tube, and any process emissions or off gases are captured from the top, depending on the application. Next slide, please. So we've got multiple technology applications under various stages of development within the business. On the left-hand side, you can see a commercial magnesite operation here in Victoria in Australia, and that's been running since 2013. We also have our lilac business processing cement, meal, and limestone with facilities commissioned in Belgium in 2019. And of most relevance to today's discussion, we have our pilot facility in Victoria that's been used to develop the processing of various minerals, including manganese, spodumene, calcined clays, alumina, and in particular, iron ore fines by means of hydrogen reduction, which is the Zesty technology that we're talking about in this presentation. Next slide, please. So decarbonising iron and steel is a huge challenge, as has been mentioned in the previous presentation, with significant international focus. 8% of global CO2 emissions come from processing iron to make steel. 80 to 85% of those emissions come from the iron reduction step. And 53% of global iron ore supply comes from Australia. and within that supply, 96% of Australian iron ore is hematite. So this highlights the relevance of the study work we've done to enable the development of a zero emissions iron and steel reduction technology that we call Zesty. Next slide, please. So what is Zesty? Zesty utilizes the platform technology we have within Calix that I described earlier with the introduction of hydrogen to reduce iron ore. The process can be easily renewably powered. The indirect heating enables hydrogen to be used for reduction only, no combustion. It's a fines-based process. The fines are introduced at the top of the process. The hydrogen is introduced in the bottom and moved upwards. And as the hydrogen moves through the vessel, the hydrogen strips the oxygen from the iron ore as it passes in counterflow. And the product exiting the process is a direct reduced iron product that's consumed in downstream steelmaking processes. Next slide, please. So Zesty technology is relevant to the entire steelmaking process. Zesty can help to decarbonize multiple processing pathways that can utilize DRI, whether that be blast furnaces, where research has suggested that DRI can be used as a, say, a 25 to 40% of the iron input, as Andrew mentioned in the previous presentation when discussing different feed mixes for blast furnaces going forward. And also electric arc furnaces, where a combination of DRI and scrap can be utilized. And as explained by Ian previously, the incoming ore type and quality is key here, given the operational tolerances of an EAF. The Zesty process is less energy intensive. Sorry, I'm still on this slide. Thank you. Zesty process is less energy intensive than conventional iron making processes and does have a much lower emissions intensity due to the absence of fossil fuel-based fuels traditionally used for heating and reduction. So I hope that provides you with an overview of Calix and where the technology fit is in the topic today regarding the feed study. So next slide, moving on to our feed study. So the objectives of the feed study were to develop the engineering and design to a feed standard to deliver a 30,000 tonne per annum Zesty hydrogen direct reduced iron demo plant. This engineering and design has been supported by an expanded ore testing program at the Calix pilot scale facility in Bacchus Marsh, Victoria. The purpose of the study was also to advance technical and commercial readiness of an alternative hydrogen-based DRI technology and to deliver an estimate of the levelized cost of producing briquettes of hydrogen-based DRI using iron ore fines of low grade hematite or hematite goethite blends, typically found in the Pilbara here in Australia. The objective of these studies is also to provide further knowledge to industry regarding the available H2 DRI technologies, and also to develop capital and operating costs that can inform the process for Calix to reach a final investment decision to go ahead and build the 30,000 tonne demo plant here in Australia. Next slide. So our feed study yielded the following results, supported by the pilot testing program that concluded in running over 130 tests with 9 different Australian ore variants. And we found that the demonstration plant could produce a green HBI at a cost that's approaching the range reported for conventional HBI production. You can see the figure there on the right of US dollars 410 to 520. Zesty can also reduce the emissions intensity of reducing iron ore the conventional way from around 1.89 tonnes of CO2 per tonne of iron to close to zero in certain applications. Zesty's got the ability to bypass traditional pelletizing, sintering, agglomeration methods, so saves on considerable capital and operating expenditure. There's a low consumption of green hydrogen because we don't use the hydrogen at all for combustion due to the indirect heating of the vessel. The hydrogen is only used for reduction, and that hydrogen that isn't consumed can be recycled through the process. The indirect electric heating is highly efficient heating method And the Zesty process economics are expected to improve further as we scale the technology and reduce capital intensity, including the cost of carbon, which would further enhance the economics as those carbon costs are further developed in different parts of the world. Next slide, please. So just focusing on the testing for a moment, you can see from the chart that many of the tests fell within the target range of metallization for DRI feed acceptance into downstream blast furnace and melter processes, and also in some cases the higher range for an EAF. There's always a few outlier results when undertaking testing, and these are typically associated with testing a few of the variables, making some tweaks in a pilot facility, such as changing the temperature or the hydrogen flow rate. So we did 130 tests, 9 different ore supplies. We achieved metallization up to 98% in the higher case. We used a range of low-grade ores as low as 53% iron. We processed iron ore fines with a range of 50 micron to 500 micron. The system can be tuned. There's a number of conditions we can adjust to achieve commercial grade hydrogen-based DRI. And our pilot scale facility is an 18-meter vertical tube, and we've calculated that the demonstration facility would be around about 36 meters. So it's worth noting that the pilot facility we have in Bacchus Marsh has not been custom built for hydrogen reduction. It's been used, as I mentioned earlier, as a multi-purpose facility for different mineral applications, and it's been retrofitted to pilot the hydrogen reduction of iron ore. So as such, the design parameters such as tube length were fixed, whereby with the demonstration facility going forward, we can customize that tube size and length specifically based on the results we've seen in this program, so that we can maximize the residence time to achieve higher metallization results going forward. And there's other design specific improvements that will also be possible when it comes to material handling, etc. And I'm also delighted to report that we've successfully produced a briquetted DRI that for a first pass is within touching distance of the industry guidelines with regards to density. And you can see the picture of the briquette that we've produced as a result of this testing program. Next slide, please. So other key highlights and findings from the study confirm a process system with flexibility designed to accommodate a wide range of iron ore feedstocks. Zesty's low cost of production is driven by efficient hydrogen use, efficient electrical heating, and the elimination of additional steps to achieve an H2 DRI product. The feed study and cost estimations considered 2 operating scenarios. So one would be over the fence supply, so potential location near to hydrogen hubs that are being developed within different states of Australia, but also the fallback alternative of in-house electrolyzer within our own project development. Total energy requirements of the process are projected to be 4.2 to 4.6 megawatt hours per ton, inclusive of the hydrogen production requirements. And the hydrogen production requirements is approximately 75% of total power, with the remaining 25% used for the indirect heating of the vertical furnace. We've also undertaken sizing and specification of the roller press to allow production of HBI, as you see from the samples we've generated. And those products can be tested in downstream steelmaking processes. And as I mentioned, the initial briquettes are highly encouraging. Next slide, please. So the feed study program has been a critical activity for us towards FID for the 30,000 ton facility. So why 30,000 tons? We see 30,000 ton nameplate as a representation of a full-scale implementation of a single reactor tube, and that will form the basis for further scale-up, which is essentially repeatable modules in multi-tube configurations. The demonstrator will be capable of producing significant volumes of hydrogen-based DRI for further downstream testing in the steel production value chain. And this demonstrator provides a great opportunity to align with other downstream melting developments, as described in the previous presentation, that are currently underway in Australia, providing bulk quantities of DRI and HBI feedstock to support the development of green iron and steel production domestically. Next slide, please. So on to the next steps. The study confirmed CapEx and OpEx figures for an operational demonstration period. Those figures remain confidential, but the next steps include finalizing site location, complete with the required access to power utilities and hydrogen production, achieving our FID supported by required funding structures, continuing the development of the pilot testing that we will continue to do at the current scale we have available to us in Victoria, and then further enhanced with this demo plant. So completing engineering, procurement, construction activities, and then also establishing agreements with industry partners for the supply of iron ore and also potential offtake for the HBI for consumption downstream. After a period of building, then we'd go on to commissioning and a decent period of operational production. So finally, I'd just like to take the opportunity to identify further enabling factors for an operational demonstration plant that requires support of government and industry. So certainly delighted with the recent news last week for extended federal government investment for hydrogen production, development and skills across Australia. We'd also require measures to deliver a reduction in the levelized cost of renewable electricity across Australia. And we also need bulk access to bulk quantities of iron ore feedstock for use in the proposed facility, and also potential use of port infrastructure as may be required depending on the location. We'll continue to partner with iron ore producers in both upstream and downstream, with the iron ore producers in Australia and also overseas, and the steelmakers. And also, finally, to close, I'd like to thank our partners that have been with us on this journey to date, and also thank you all for attending today and listening to this presentation. Thank you.
Thank you, Chris. The Zesty technology definitely seems to be very promising. So yeah, I guess we'll look forward to hearing about the demonstration plant in future. So we now have our first Q&A session, and I can see already a few questions coming in the Q&A box. I actually forgot to mention at the beginning that you can like questions, so we can kind of prioritize the most popular ones. I can see some of you have already done it. But as mentioned at the beginning, totally happy to take questions through the Q&A function, but also feel free to raise your hand if you want to come off mute and ask your question. We definitely want also to have a little bit of interaction if possible. But while people are warming up, I guess we can start with a couple of questions that are in the Q&A. That might be the most popular ones. Tom, would you like to come out of mute and read a couple of them?
Yeah, absolutely, Lisa. So 2 questions from the chat that were directed both to BlueScope. During the transition period from natural gas to hydrogen, do you see scope to use hydrogen natural blended gas?
Yeah, that's something we've actually considered. We did look at a feasibility study of building a 10 megawatt hydrogen electrolyser at Port Kembla, and we had 3 outlets for that, and one was blending with natural gas. Currently in steelmaking, it's certainly at Port Kembla, natural gas is not actually a big part of our footprint, but in our midstream sites, which is our cold rolling, painting and coating sites, that it is more of a proportion of our total emissions. So it is something we're sort of considering. There's probably better people than me that talk about the technical limits. That's like roughly 10%, I think, is by volume is what the nominal figure is, that without changes to combustion equipment. But yeah, it's something we haven't, we're still considering, yes.
Okay, and I'll ask a follow-up about biochar. So besides access, which you made clear, what are the barriers you see to increasing the percentage of biochar use versus PCI?
Yeah, I guess there's no real barriers. I mean, if you look at the prehistory, steel was made with charcoal. So in theory, there could be 100% biochar. But I guess in a modern facility like ours, we haven't trialed that. So that's probably not a fair comment. The tonnages we're talking about are enormous. So for us to get a high proportion, we're going to need a lot of biochar. So it's going to be in a staged process anyway. And I probably should mention too, for those who don't know, there's two different types of coal we use: metallurgical coal and PCI. We call it PCI, or thermal coal. So the biochar is replacing the thermal coal proportion. So that's only a proportion of our coal, if you know what I'm trying to say.
Thank you. Thank you, Andrew and Ian. So I cannot see any hands up yet, so we might keep going with the questions in the Q&A box. Tom, would you like to pick another one?
Absolutely. So just continuing with the biochar theme, we had a question around the emissions reduction potential. They wanted to, Jasmine was wondering if you could share any numbers.
Yeah, so I mean, it's fairly simple. We're replacing coal, so it depends on the type of coal, but it's 2.9 tons of CO2 per ton of coal. So you can do the maths yourself. If we charge 100,000 tons, it's nearly 300,000 tons of CO2. There's an assumption there that the coal quality is equivalent to the biochar quality, but generally that's the numbers.
Awesome, thank you. I might actually jump in now. I can see there is a very popular question for Calix for you, Phil. So Chris, sorry. So what do you estimate the equivalent gigajoule per ton for the process to compare with traditional or the known kind of steel making routes across all the plant?
Well, I think the big difference is certainly the absence of the use of coking coal in the reduction, the high energy intensive process. Our technology is really down to the electricity required to produce the hydrogen in the most part, and then the indirect heating of the tube. So we're underway with a lot of CVP analysis with all the various different inputs, and we hope to be able to publish that information further in the near future.
Yeah, thank you. And also kind of related question around Zesty, in particular around the benefit of Zesty technology compared to the fluidized bed route.
Okay, well, I'll give a generous answer here with knowing there's a few colleagues on the audience that work closely with me on fluidized beds. So I guess in terms of the Zesty technology by comparison, it's a low pressure system. So it doesn't have the complexity of having to stabilize the fluidized bed itself, and also it's got the ability with the nature of the product flow. We can turn down and ramp up extremely quickly, so we can switch the feed off, and then as soon as the material is out the bottom, so our residence time is very short. It's tens of seconds. And as soon as the feed is off, then the unit can be maintained at temperature, and this is particularly important when using renewable electricity, because we can match load demand by switching off very quickly, knowing that there can be significant spikes in energy pricing profiles over a 24-hour period. So quick turn down and ramp up also.
Thank you. So it seems we've got very shy audience today, no hands up, but we still have a lot of questions in the Q&A box, so we might keep going. Tom, would you like to pick another one?
Yeah, absolutely, Lisa. So I might keep with the theme and continue to direct my questions to BlueScope. We have a question around supply of natural gas in the long term, noting the tight gas markets on the East Coast.
Yeah, that certainly is a concern. We are talking to people about that, government, etc. Yeah, natural gas is very expensive in Australia, and that's why I mentioned before that DRI is produced in places where it's cheap, i.e. Middle East and the US. I've been around it long enough to know that it was interesting. 20 years ago, gas was more expensive in the West Australia, than it was on the East Coast, and that's flipped quite substantially. So, yep, cost of natural gas and supply of natural gas is a big factor we need to address.
Thank you. So we might keep going if I don't see hands up. A question for Chris. So has Calix conducted any reduction kinetic studies on the fine ore in the reactor? And also, how long does it take for iron ore to be reduced in the reactor? Very specific questions. We can always follow up offline if we don't want to share too much. But
yeah,
that
first one's very detailed. The answer is yes, we are doing the kinetic studies. There's the shortly published will be the results, the detailed results of the HILT program. That was part of the extended program here in the testing that we did to support the feed study. So there is some turbulence in the process with the counterflow nature of the hydrogen passing through the ore as it travels down the tube. It's essentially because it's a low pressure, slightly positive pressure process, essentially a gravity fall through the tube. So if you can imagine, if it was pebbles, they would drop too quickly, which is why it's a fines-based process, so there wouldn't be sufficient residence time to reduce. But below 500 microns, there's a residence time, as I said before, it's tens of seconds as opposed to minutes or hours in this process. So it's a very short residence time compared to other technologies.
Thank you, Chris. I go one more and then I'll maybe give Tom the opportunity to jump in again. So question about hydrogen. So I guess for you, Chris, again, but also BlueScope team, if you want to jump in. So what do you see as current barriers of using renewable hydrogen in DRI? Top two.
Yeah, well, certainly at the moment, we know that in the short term, the cost of producing green hydrogen and the availability of green hydrogen is limited. So, and this is impacting us during this demonstration period here in Australia, and it's also been publicly commented as a challenge in Europe as well. So in the period whilst we're developing these technologies, we're having to consider the high cost of producing the green hydrogen and when that will be available in the volumes that we need.
Yeah, thank you. And BlueScope, if you have any insights to add, that's also obviously much appreciated. I think we'll also talk about a little bit more about hydrogen and the barriers and things like that in our next presentation with Nicole. So we'll probably get additional insights there. Okay.
Yeah, I was just going to say, Chris answered that really well. Yeah, cost is quite a big barrier. Absolutely.
Yeah.
Yep.
Okay, thanks. Tom, would you like to jump in again?
Absolutely. So I'll just take this opportunity while I have the mic to remind our audience we have the relevant reports from these projects on the knowledge bank. There will be details there that may be helpful for you. And for any latecomers who didn't hear it at the start, we will be making this presentation available on the knowledge bank as well. It's being recorded. So now the question that's come again to the Steelworks, there is a question around the long term, so post 2030. Is there any rough estimate of how much annual hydrogen consumption is expected and which processes it would be used for?
I think it's a bit early to say, to be honest. So we're currently looking at, as I mentioned, doing a pilot plant, potentially with a DRI shaft furnace as well as an ESF, but that's still to be determined. And Yeah, I guess we really will be focused on natural gas to start with, but hydrogen's longer term. But perhaps that trial plant can give us a better indication of exactly how much hydrogen we need.
Thank you. And maybe going back to the kind of biochar topic, Andrew, you mentioned there were some issues around sourcing biochar. Someone is interested in understanding where was your biochar sourced from. I guess you don't need to give the details, but generally speaking, I guess the most interesting part in the question is, do you see it as a scalable supply chain? So how does it look like in future? Can we potentially increase volumes?
So perhaps I start, because part of the project was we really did struggle to find the amount of biochar that we were looking for. So, for us, 1,000 tonnes is very small, considering if we think of our PCI plant that uses 1,200 tonnes of coal per day, it was less than 1 day's supply. So if we were to replace all of that. So just to give you scale, but yes, we did struggle to find some, and that really reflects the current, I suppose, supply chain of biochar in Australia. Tends to be smaller supplies for, I suppose, different purchase, agricultural and some of the other purposes that people want biochar for at the moment. And then Ian's probably...
Yeah, I mean, it's a great question. Yes, it is a concern, the scalable supply chain. I mentioned 100,000 tonnes. You're going to need the yield for biomass to biochar is quite low, typically 30%. So you need to triple that. So when I started looking at it, and I've been looking at it for a couple of years, I mean, forestry is an obvious option. There's invasive native species, which is an interesting one. We also have some noxious weeds of national significance. So all those are on the table, and they are quite big tonnages. But yes, that's a part of the interesting thing about biochar is not necessarily the technology to make it, it's also the feedstock. Yep.
Might continue on the theme for a second. There's a question around the role and potential of biomethane to replace natural gas.
Yeah, that's it's come back into my awareness quite substantially. It seems to have dropped in price. When I first started looking at it a couple of years ago, it was way higher than natural gas, and that margin has dropped substantially. So I'm starting to get more interested in that. Yeah.
Perfect, thank you. So there was a question around carbon capture. So anyone keen to take that? The question was around, during the transition from natural gas to hydrogen for DRI, do you think CCU will play a role when natural gas is used at scale?
Yeah, it's something we're looking into. So Port Kembla itself is not what's the word I'm looking for? Geologically suitable for carbon capture and storage. It would have to be offshore, which doesn't help the cause. It's quite expensive, but it does actually line up somewhat with hydrogen. So both options are really expensive. But yeah, we're looking at it, but it's not sort of our primary focus at the moment.
Okay, thanks. I might go with one question for Chris, and then I'll go back to Tom. We'll take a few more questions, and then we might go to the next presentation and allow a bit more time for questions at the end, so that Chris, Paul, and Ian can have a break. A very intense time. So Chris, someone is interested in the financial analysis and whether that analysis, as part of that analysis, do you consider the capex of hydrogen electrolyzers and how big the impact of that is in your financial analysis?
Yeah, so part of the for the demonstrator. So in the short term, our preferred option one is to receive hydrogen at a cost per kilo. So we've worked that into the operating costs based on the information we're gleaning from the market. in Australia. The fallback option would be to include the capex for the supply of a hydrogen electrolyzer within our own scope. So we've also done that work in the capex part.
Yep,
And
cool.
as I commented before, the specific question on the current challenges with green hydrogen is that there's obviously the immediate term pricing. However, this is first of its kind demonstration where costs are always expected to be higher. And in time, as renewable electricity becomes more available and ultimately the price reduces, as I mentioned in the last part of my presentation, as the renewable electricity price comes down, that directly supports the cost of green hydrogen coming down as well in the long term. So there's plenty of information in the industry regarding predicted costs of green hydrogen in the future at the time when we would be commercially operating these facilities.
Yeah, cool. And sorry, just before going back to you, Tom, there is one very detailed and technical question. So not sure if you want to share these details, Chris, but I'll ask anyway. Is the temperature distribution in the reactor uniform?
Yes.
Yes.
It is.
Is it done? Awesome, thank you. Back to you, Tom.
You took the question I was going to ask, Lisa, but I'll go next
That was
on the list.
interesting.
So,
Yeah.
so maybe just to expand on that, so the pilot facility that we have in Bacchus Marsh is 18 meters in length, and we have 18 temperature zones. So as I mentioned in the presentation, we have the opportunity to make adjustments. So we have a very clear pinpoint feedback on the temperature at each 1 meter zone, and that's tightly controlled. So we have a real tight control on operating temperature, given the nature of the technology.
Thanks, Chris.
I'll jump in and ask a question from someone with cement background. They're wondering about the mechanical integrity of the tube and sleeve arrangement, and particularly how it's protected under high heat. Again, detailed answer as you can. I'll also just flag as the Q&A section is running to the short, if any of these questions haven't been hit, if our presenters are feeling generous, they might be able to get into the Q&A and answer you directly. So the question to you, Chris, to the extent that you're able to answer it, is for someone from a cement background, how are you protecting the tube and sleeve arrangement and the mechanical integrity of that under high heat?
Yeah, that's not my specialist area, but yes, it is a refractory-free internal tube, and the refractory is on the outside of the vessel. And there's obviously movement and expansion as the system is heated up and operated. So all typical design considerations are taken into account to allow for thermal expansion of the tube.
Thank you. So we've still got a few questions. I might get 2 or 3 more, and then we keep going, noting that we can also go back at the end. So question for BlueScope. Presuming the existing NG facility to upgrade to hydrogen, are there any feasibility study in progress looking into it?
Really understand that. What was the start of that question? Sorry, what hydrogen with the pilot?
With the natural gas, the existing natural gas facility to upgrade to hydrogen. So I think definitely in the future you are looking at, well, I mean, as you mentioned, you are looking at integrating hydrogen there. Any additional details in terms of the feasibility of that?
I guess, as I mentioned, we really focused on natural gas. We would like, and we might be able to use hydrogen as a reductant potentially in the trials. But yeah, the focus will start with natural gas. Yeah.
Okay. Tom, do you have any final question before we move to the next presentation?
Yeah, I was going to ask a recent question just on that topic. So again, for BlueScope, with the announcement of a tax credit for green hydrogen production, $2 a kilo. Do you think that shifting directly to green hydrogen is possible instead of starting with gas?
Yeah, I don't have the figures in front of me, but that doesn't sound like a huge amount. I think it would have to be significantly more. I think, yeah, I know the New South Wales government were looking at different numbers, and they seem to be a lot higher than that. But yeah, no, that I don't think that would make the difference. That wouldn't make or break us.
Okay, thanks. So
I might jump in and
yeah.
ask one more on the commercials, if I can be so bold. We had a question around the max cost of delivered biochar to be commercial.
Yeah, I think I'll pass on that one. That's sort of commercially sensitive.
That's fair enough.
Fair. Okay, so we might move on. And as Tom said, if there are any unanswered questions and the speakers would like to take them, that would be great. If not, we can also go back to them at the end of the webinar or take them offline, again, if the speakers are keen to provide additional insights. So I think now I would like to welcome Nicole Rook, who is the CEO of the Minerals Research Institute of Western Australia, who is going to talk about some key figures from their Green Steel Opportunity Report, and will also give us a quick demo of the value chain model. Hopefully the technology is with us. So over to you, Nicole.
Thanks for that, Lisa, and it's great to be joining everyone today. I'm joining you from the lands of the Whadjuk Noongar people, who are the original custodians of the land on where Perth is located. I'm really keen to be pleased to be able to showcase again the work that we have been doing. We started the journey of the discussion here in Western Australia about 4 years ago about what our potential opportunity was for us to be able to support the steel industry to decarbonise. So what I'm going to take you through today in the presentation is to briefly talk you through our model and value chain and what the 5 pathways were that we considered, some of which are certainly pathways that we've just heard Calix and BlueScope that they're giving consideration to certain elements of it. I'm also going to look at what were some of the decarbonisations that we identified, and noting there were a couple of questions around where could hydrogen be used in the process, can certainly touch on that, and where we looked at where that hydrogen use is a potential. I'm then going to look at and provide an overview of what we saw as the capital requirements and the levelised cost of what those 5 pathways were, and give some comparisons for that against the fossil fuel options, to be able to signal and understand what the sheer size and scale of this opportunity is for Western Australia, and what the capital investments are that are going to be needed if we want to do further onshore processing of our iron ore here in Western Australia or elsewhere around Australia. I'm then going to touch on some of the opportunities and challenges, and then finally, as Lisa indicated, I'm going to hopefully be able to show you our online demo, our online model, which has the ability to be able to run some different scenarios. So just moving along, looking at our decarbonisation opportunities that we had. The work that we did in partnership with GHD and ASIL Allen sought to establish a steelmaking value chain and be able to create individual modules along that, units along that we could then run some different scenarios. The 5 different pathways that we looked at then progressed along that value chain. So the first pathway that we looked at in terms of how Western Australia could engage and support the steel industry to be able to do that decarbonisation was effectively just progressing down the pathway of producing iron ore, doing iron ore mining in a green way, so electrification of the process. We then looked at the option of progressing further down the value chain beyond mining to a green pellet product, then using those green pellets converted to a HBI product using fossil fuels before moving then to a completely green HBI product using hydrogen, and then also looked at the full production of green steel in Western Australia, but could equally be anywhere else. The figures that you can see on the screen demonstrate what the different decarbonisation potential is at each of the phases along that value chain. So the figures in red relate to hematite ores, and the figures in red relate to magnetite ores. We chose, as part of doing the piece of work to go through to green steel, was certainly looking at the electric arc furnace of the as the green steel solution, but at all other points of the steelmaking value chain, we looked at what was needed to be able to decarbonise the blast furnace route. And I think it was Andy that mentioned that over 70% of the world's steel is created through the blast furnace mechanism. One of the things that I will just briefly touch on, and there are a number of questions around the use of natural gas as part of a processing solution. When we looked at the green pellets converted to a HBI product using fossil fuels, if that is an activity is sought to be onshored here in Western Australia, it certainly has a significant opportunity to be able to reduce downstream emissions quite significantly, in the order of, I think it's close to 65%. However, the real challenge for that for Western Australia is that then actually onshores emissions here in Western Australia. So while it is of benefit to the steel industry globally, it does have implications from a West Australian policy and industry perspective. And there's certainly been commentary in recent times or in recent days regarding the size and scale of emissions produced here in Western Australia. But where we landed as part of doing our assessment is really that where there's opportunity for Western Australia is the supply of alternative high-grade iron feedstock products, so that we can then help support steel industries, whether they be elsewhere in Western Australia, steelmakers elsewhere in Western Australia, or overseas, to be able to then produce the final products. When we looked at the various decarbonisation options, what we certainly looked at was where was there opportunity to replace fossil fuels in that supply chain. We looked at the opportunities where there was power generation, whether it was in areas of transport, and the various other items on the screen. By far the greatest opportunity for the steel industry to be able to decarbonise their options is through the finding alternative uses for the replacement of fossil fuels in blast furnaces in steel production. And certainly some of the two discussions and presentations by Calix and by BlueScope is where their key focus areas are, is finding alternative solutions to that. Of those options, where we looked at where there was the potential use for green hydrogen was certainly in and around it being used as an alternative fuel for transport, as an alternative and replacement of sintering to be able to produce green pellets, as an alternative in the blast furnace in steel production, but then also looking at it in that option of using a greener iron product as well. So you can see there that there is the different options have different implications or opportunities for change, but they also come with it with quite significant capital requirements, but also some significant technology changes as well. Just moving on to capital requirements. What we looked at as part of our work was being able to understand what it would take to be able to support the onshore processing of our iron ores here, and what across all of the different categories, what were the capital requirements for that? And we took into account as part of that the cost of producing hydrogen, the cost of the deployment of the renewable energy solutions, the capital costs associated with building pelletizing facilities, shaft furnaces and electric arc furnaces in all of the different cases. So what you can see there on the screen is, and that doesn't include the renewables, the cost of renewables, are the capital requirements. So starting from, I'm looking at my screen on the left-hand side, the first two columns, on the very left is the fossil fuel option, and then alongside it, it is the green iron mining. And when you look at the first options of green iron mining and green pellets, that actually with the cost of renewables as they are today, then what we see is that it is actually cost comparable at this point in time to be able, from a capital perspective, to be able to progress down those value chains. Once you start getting into production of green iron and green steel, the capital requirements start going up significantly. And so the information, the top row that you have on your screen is related to hematite, and the bottom row is related to magnetite. So while and at a rate of 50 million tonnes of mined ore. So this is the same input rate, but obviously the volume of steel that is produced from those 50 million tonnes varies considerably. Just somewhere in one of the questions, there was a question around what were the annual or requirements, hydrogen requirements. As part of our model, we sought to be able to get an understanding of what those annual hydrogen requirements. And just by way of example, if you were wanting, our model considers that if you wanted to ship 1 million tonnes per annum of a green HBI product, then what you were looking at needing was 69 kilotonnes per annum of hydrogen. If you're but noting 1 million tonnes of a ship product when the steel industry produces in the thousands of million tonnes per annum of steel, that it's a significant volume of hydrogen that's going to be needed going forward. In trying to understand the various pathways, what we then also looked at was the levelized costs of the production of those pathways. And again, on the slide, this is looking at processing 50 million tonnes per annum of mined ore, both for hematite and magnetite. And again, what we can see is that, price competitiveness for green iron mining, as well as the production of green pellets compared to the existing fossil fuel pathways is certainly comparable. But once you start moving into that iron ore, into the green iron in HBI form and green steel, that there becomes quite a significant differential between the levelized costs. What's really interesting when you look at the pillar, the column in the middle of the graphs there, that's the graph showing the green pellets converted to HBI using fossil fuels, so using natural gas. And what you can see that actually that as an option is certainly very price comparable when looking at producing fossil fuel iron in a pig iron form. So there is a real argument that use of natural gas can not only help reduce emissions here today, if the steel industry were able to adopt greater utilisation of natural gas while the technology is developed to be able to progress for greater use of hydrogen, but it does also come out as a price comparable solution. What's key when you look at all of those options, and again, one of the questions was around the price of hydrogen, it becomes imperative and fundamental to the changing price point. So looking at under our model, the production of green pellets becomes price competitive versus traditional methods when the price of hydrogen reaches approximately $2.80 a kilo when you're considering processing magnetite, but around $1.50 a kilo when you're processing hematite. If you're looking at the green iron in the form of a HBI product, to be price competitive, you really need the hydrogen price to reach around $4 a kilo and then finally, for green steel, our model was demonstrating that you need the hydrogen price to be able to reach $3.20 a kilo. So there's certainly a significant way to go. Our price point for starting in our model was $7 a kilo for hydrogen at this point in time. If I can just move on to the next slide to look at what we have versus what's needed. I mean, certainly here in Western Australia, we've got the iron ore, both in magnetite and hematite form. We already supply around 30% of the steel industry's iron ore that they require. And so what we're seeking to be able to do what's needed is to be able to look at how through the adoption of new technologies are we able to improve the grade of that product as well as remove the gangue prior to export. And so in that way, being able to supply an alternative iron product into the steelmaking market. Western Australia's got lots of fantastic opportunity in relation to merging green electrification of production processes using renewable energy. But actually, there becomes significant challenges in delivering that electricity generation, green electricity generation in the locations that it's needed and at the scale that it's needed. For not all of the where there's the opportunity to be able to progress some of the processing options, or where some of the mining happens, where there may be some of the downstream processing is not necessarily where there's the best renewable energy solution. So the cost of transmission and the provision of additional transmission infrastructure will be really important going forward, in the same way with new port and rail capacity as well. Key to understanding what was needed to be able for Australia to progress further down the value chain using West Australian iron ores is also the supply of water, not just power, but also water. And along with that, what are the land infrastructure that's needed as well, industrial land. And our model sought to be able to start giving some insights into that. So whether it be within companies or within different organisations, that they can start getting some clarity on what is needed. If I just move on, looking at what we're doing, what MRIWA currently has underway. We have been we're currently doing a pre-feasibility study into a flexible iron making pilot plant, and have been having a number of discussions with different parties to understand what is it that's needed to be able to trial and blend Western Australian ores and their suitability to be able for use in other processing options, whether it be electric smelting furnaces or electric arc furnaces. And we are currently working on doing a potential upgrade to our model to be able to help people have access and be able to run different scenarios, just to get some insights into all of the matters that I've just outlined. We're a member of the HILT CRC and are partnering with a number of different organisations and looking at what projects that progress some of the technology solutions that are currently creating barriers to being able to progress further down the processing of green iron or green steel. And you can see those projects listed on the screen. Just to close out, what hopefully happens on the next slide, and if the team activate it. So this is our green steel value chain. You can access it via our website. From that, it has a number of pre-programmed different scenarios that you can choose from. And then in the box immediately below it are some fields that you can then seek to tailor for your own purposes, whether it be volumes or price points that you want to run different scenarios. It provides a summary of what the different fixed parameters are. By submitting that information, then you can get the results from that model. And so what that will show you are things like what the levelised cost is, the emissions profile of the various scenarios that you've selected along that value chain, what the capital requirements are, power, water, and importantly, what it also shows you, for those of you that are interested in knowing more about the hydrogen requirements, is that it will then give you some indications, depending on what the scenario is that you've selected, in terms of what the hydrogen requirements are for that particular scenario. So that is our model. They're some of the key findings that we had from the completion of that model, and we're certainly really keen to continue to work with across government as well as with industry partners to be able to see how do we progress the technology development to find those solutions to the benefit of Western Australia. So thanks for that. You've got a QR code to be able to access our model, but you'll be able to also get that information at a later point in time. Back to you, Lisa.
Thank you, Nicole. Absolutely super interesting analysis of all the different decarbonisation opportunities, the economics involved, and especially what is required really to kind of catalyze this transition to net zero. A lot of insights on hydrogen. Thanks for that. It seems that the audience is really obviously interested in the topic, and I'm sure we'll get to some questions later on. But now, last but not least, I would like to hand it over to Tanya. Tanya Hodgson from ARENA, who is an investment manager here at ARENA. She's going to give us a snapshot of the iron and steel R&D project that have recently been announced as part of ARENA's track program. But I won't say more. Over to you, Tanya.
Perfect. Thank you so much, Lisa. So I won't pretend to be nearly as close to the expertise of the folk who are actually taking these projects forward, but I am very excited to talk to you about what ARENA has funded in our most recent research and development rounds. So if we go to the next page, ARENA recently committed nearly $60 million worth of R&D funding to a total of 21 projects across 17 recipients, so a couple of universities with more than one project or focus area. And those grants ranged from $1.3 million to $5 million, which was the cap on the round design. And so what's super exciting is that together that unlocked a total of over $200 million of R&D investment across those 21 projects, which I think is a really exciting kind of boost and increase in momentum in both hydrogen and iron and steel research. And encouragingly, there was also quite a lot of good diversity across the recipient group. So we did see a lot of universities, but there was also research organizations, startups, and kind of bigger companies as well that were investing as the lead applicants. And so obviously this is a iron and steel focused webinar today, and I'll focus on the projects under the iron and steel round. But I did want to call out that we actually ran the hydrogen R&D round in parallel to iron and steel. And the logic there was that there's quite natural synergies between the two. And obviously we've heard today a lot about how important hydrogen can be to some of the low emissions iron and steel pathways, and how it's critical to get the cost down in order to actually see some of those technologies become more commercially viable. So the R&D round for iron and steel focused on novel and innovative low emissions technologies using Australian iron ores. And that round awarded close to $25 million worth of funding to 8 projects. And then the hydrogen round focused on accelerating innovative and renewable technologies across the hydrogen value chain, so production, storage, and distribution, but not the actual end use cases of hydrogen. And that awarded $34 million to 13 projects. So even though I'm not going to get deep into the hydrogen projects today, if you want to find out more, this is all available on ARENA's website. So if you just chuck, ARENA R&D funding in Google, that list will come up. Otherwise, we're also happy to pop that in the chat as well. And you can see the scope of the work, the funding awarded, the lead recipients. So if you want to find out more, please go and do that. So I wanted to spend a minute on the funding rationale for the iron and steel round before we get into this page. So if we just stay on the previous page for a sec, thanks. So, we've already heard from BlueScope and from Calix that Australia is the largest global exporter of iron ore. We also heard that there's some challenges with the iron percentage or the grade of the iron ore that comes from the Pilbara, which makes up the bulk of our export. So we know that a lot of the emerging low emissions iron and steel pathways typically rely on the availability of higher grade ores. And when we talk about low and high grade, we're kind of talking an iron percentage above 65% in your feedstock materials. And that availability is globally constrained. So we know that in order to kind of shore up the continued export of Australian iron ores, we have a key role to play in figuring this out and in kind of progressing the global low emissions iron and steel value chain. And that's for our export market and to decarbonize our own domestic steel production. So we know that investing in innovative R&D is a critical enabler to being able to do that and being able to develop the technologies to transition to that net zero future state. So at a very high level, there's kind of 2 primary approaches to addressing that ore challenge. You can either go upstream and optimize the upstream process so that you get to a feedstock that's higher grade. and then is compatible in whatever process route that you're choosing. Or you use the feedstock as is and think about optimizing the flow sheet of the route that you address to deal with the impurities or the gangue, as was mentioned earlier. So the funded projects that we look at address this both of these kind of angles or approaches, and covered, iron ore processing, iron making, and steel making tech. So we can get into those on the next page. Perfect. All right, so before I get into the specifics of the project, you can see in the chart on the left-hand side, which has got the grant funding amount and then the total project amount just split out by kind of the rough technical route or technology focus. So if you go from bottom up, you'll see that there's 3 projects that look at optimizing the hydrogen direct reduction of iron. There was a project looking at developing low temperature electrochemical iron ore reduction, one looking at reducing blast furnace emissions, and then 2 looking at improvements in that upstream step in agglomeration and beneficiation, and then finally 1 project optimizing the use of steel furnace slag. So it's worth noting that the projects were assessed based on their total emissions abatement potential and emissions intensity, as well as kind of continued relevance and contribution to net zero iron and steel making pathways. And partial abatement solutions were considered on the basis that they could significantly reduce emissions in the medium term as net zero pathways emerge. So to give you a bit of color on the 8 projects that were funded, and I'll flip and go top down so it's easier to follow. We had Macquarie University project, which is going to pursue a process for the separation of higher value components. So looking at iron, calcium oxide, and phosphorus from the steel making furnace slag so that you can reuse those materials. And that project is being done in collaboration with Hammersley Iron. It's going to run for about 5 years to 2029, and you get approximately 25 kg carbon dioxide reduction for every ton of steel. The next project is being led by the HILT CRC. It's got a fairly sizable consortium, including Roy Hill, Fortescue, Curtin, and a couple of others. And this looks at improving the commercial viability of beneficiation. So we know beneficiation is expensive. It's looking at taking ore quality sort of 56% and below up to above 67%. Using reagent replacement. So for example, using reagents from seawater, reverse osmosis brines, and also producing valuable byproducts so that your cost stacks up in a more attractive manner. And this project is also going to go to 2029. Then we've got CSIRO. They are looking at a novel low temperature iron ore agglomeration method. So instead of operating super high temperature at sort of 1,350 degrees Celsius, coming all the way down to 300 degrees Celsius, but still getting a premium high quality product so that your pelleting economics start to look more attractive. And they're doing this with Grange Resources, Roy Hill, and Swinburne to about mid-29. Next on the list is UNSW. So this is looking at decarbonizing the blast furnace by top charging the ore feedstock with injections of fine ferrous feed, hydrogen-rich gases, and also biochar into the blast furnace, looking for a 25% emissions reduction. And this has also got a big consortium. It's being done in collaboration with Rio, BlueScope, University of Newcastle, and University of Queensland, and I think 1 or 2 others. And that's also going to 2029. Then we've got MIH2, and this is a Fortescue subsidiary, which is looking at developing the scale of their solid state slurry electrolyzer which uses an alkaline electrolyte for low temperature, and that's less than 130 degrees, for the direct electrochemical reduction of iron ore to iron. And so that's kind of looking to get to a small scale pilot stage in collaboration with Deakin and Curtin, going to 2026. So pretty short term results, which is exciting. We've also got ANU, which is looking at de-risking the application of fluidized bed hydrogen direct reduction, using low-grade ore fines as well. And here we're looking at reducing costs by at least 10% and also addressing some of the risks, for example, related to particle stickiness and defluidization in the fluidized bed, as well as assessing the techno-economics of getting to a readily exportable pig iron product. This is being done with Swinburne, Hilt CRC, FMG, Grange Resources, Roy Hill, and the University of Newcastle. And then the last two on the list are focusing on a similar process route. So the hydrogen direct reduction combined with an electric smelting furnace to manage the impurities removal when you use a low grade ore feedstock. And so the University of Newcastle is looking at de-risking the metallurgical aspects of the electric smelting process. And that's going from small scale, small lab scale, so like kind of 5 kg batch testing, getting up to 200 kg smelting of direct reduced iron using an existing electric furnace in collaboration with RWTH Aachen in Germany. And then the University of Wollongong is similarly investigating the performance of direct reduced ores in an electric smelting furnace, but the approach is a little bit different, using high temperature experimental and computational modeling and comparing lump, fines, and pellet feedstock, which use up to 100% hydrogen in the HDRI process, and looking to kind of optimize the operational conditions for that electric smelting furnace. So that was a long list of a lot of content, which is obviously pretty technical, but a couple of things I wanted to call out as being really exciting here. One is that we were really impressed with the market appetite to progress work in this space. And I think that's a great indication of where Australia is at and how much focus there is, especially because this is tough, it's slow, it's expensive, it's really challenging. So overall, I think to get a momentum boost is really positive. The second thing I wanted to call out is just the range of players that I mentioned as I was going through here. And something that I think we can probably all appreciate is how challenging it is to go from doing work in a lab to getting that work out the lab. And I used to work in a lab back in the day, and so can speak to my own experience, but it's really hard to kind of navigate, you know, what is colloquially called that valley of death. And so I think it's really encouraging to see the industrial players being invested in these different technology routes as they progress. And I think that's exciting for the industry as a whole, and something that we really wanted to see come out of this process. And then the final thing that I think is exciting is because of the kind of increased focus in this area, it's a great capacity building experience to equip Australia with the necessary skills and expertise to be the leaders that we could potentially be in this space. So overall, ARENA's view is that supporting R&D projects in the space can really help catalyze significant advancement in low emissions iron and steel tech as a whole. And we're really excited to see how these projects progress. So stay tuned. If you want to get in touch with anybody who's actually doing this work, those details are on the ARENA website as well. I'll call it there.
Thank you, Tanya. Definitely many promising technology being currently tested in the Australian labs. And to your point, yes, we definitely hope to see all of them, or at least most of them, commercialized in the market in the next few years. And in terms of having more information about projects, first of all, we are lucky enough to have some of our project recipients online today who might be able to jump in and provide additional context and comments. So thanks for that. And also in the next few weeks, we will be able to publish on our website on ARENA Knowledge Bank, the first digital research poster from each project. Again, they are at the very beginning of their journey, so probably not able to share many results at this stage, but at least you can go and have a look at, a little bit more in detail what they're planning to do, their research plan, what kind of challenges they're trying to address. So stay tuned again. In the next few weeks, they should all be online for you to go and check. So I guess we're now with the final Q&A section, and I can see there are already a few questions in the Q&A box. I'll try again in case someone is brave enough to lift their hand and come off mute. We always have that opportunity. But in the meantime, maybe I'll kick off with one question that I was pretty interested. So interesting, this question is for Nicole. So people are interested in understanding about the cost. So specifically, does the LCOE per ton product include the fixed and variable cost of renewable electricity? Obviously, renewable electricity makes a huge difference. So we are definitely interested in understanding how this is taken into account.
Make sure I take myself off mute. Absolutely, it does. So in the full report, what you can do, it demonstrates what the different breakdowns are in terms of where the levelised costs are incurred, and certainly demonstrates where the impact is of hydrogen production, the cost of hydrogen production has on the levelised costs. So while it wasn't included in the CapEx slide, it certainly is included in those levelised costs. And there's a much greater level of detail in our green steel assessment report as well.
Yeah, thank you, Nicole. And while I have you there, just a quick clarification. Someone was asking, was the 30% of iron ore that is provided by Western Australia to the steel industry in Australia or globally?
Globally. So Western Australia, the iron ore from Western Australia accounts for 30% of global supply of iron ore. Yep. Sorry if I got that wrong.
I know. I guess just a clarification, and that is a massive amount.
Yes.
Okay. So I might ask one more question about specifically the ore and the quality of the ore, and then I'll ask Tom to jump in with additional questions. So there was a question, and that was already answered by another person, but I guess it's interesting to have additional insight from either you or BlueScope or Calix if they want to jump in. So how much of a factor is the ore quality in getting to target metallization? So in particular, do you see a pathway for Pilbara ores for a potential DRI EAF route? Obviously, the ore quality is an issue and it's really important when we try to understand which technology we want to use.
Yeah, and I'm happy to start that, but equally would welcome input from Calix and BlueScope, equally from my colleague David Trotter, who hopefully he's still online as well. But again, as part of our full report, we did look at what the sensitivity analysis needed to be around the different gangue, the different impurities that with the various ore types. One of the things we didn't do in our piece of work was actually look at what the opportunity was that could exist if there was blending of hematite and magnetite ores. And so that's some work that we're looking at and having some discussions on about whether actually that then helps from a carbon reduction, emissions reduction perspective. We didn't so much look at it in terms of what the metallisation was, but I see that Chris has come back on from Calix, so I might do a handball to him to answer the rest of that question.
Yeah, thanks, Nicole. Well, as you saw on the scatter that I presented earlier, we did achieve a few results that were higher than 95%, and the highest was 98. So, and that was from Australian Pilbara ores. So we've achieved it in the pilot, and as I mentioned, also the reaction time is limited due to the fixed length of the pilot facility, and there's also adjustments we can make from the results that we've had to date to fine tune with a plan to get as many as those results above the line for AAF. And of course, there's other intermediate steps that can be considered generally in upgrading the ore as part of the process as well. And whether that applies to or that would apply to hematite or also magnetite ores.
Thank you. Chris, any additional insights from BlueScope there?
I guess I'm just going to say that I know that overseas there have been trials of using some hematite in some DRI shaft furnaces, like a small proportion, but generally you need the higher grade in those processes, and that's the route we're going down.
Awesome, thank you. Actually, just a quick question for Tanya before getting to Tom. And I'm not sure whether, again, this webinar is more focused on green iron and steel, but in case you have any insights on the hydrogen side, do you know whether ARENA has received much interest in 100% hydrogen pipeline transport R&D? Is it something that we heard about or not in a massive amount?
Yeah, I guess in short, no, there wasn't a lot of interest kind of looking specifically into that area as a key kind of transport method. Whether that's indicative of what the rest of the market is doing, up for debate, but not necessarily, no.
Thank you. Tom, did you have any great questions you would like to highlight?
I have one question to put to Tanya, which is, can you speak to anything more of the 1.7 billion Future Made in Australia Innovation Fund for the commercialization of technologies critical to the net zero transition? I knew you were keen to get this one. I'll let you do with it what you want.
And maybe, sorry, Tanya, just before you give whatever information you want to give, I guess maybe clarifying for everyone that this forum is focused on sharing knowledge on green iron and steel and from our existing projects. Obviously, the Future Made in Australia Innovation Fund has been really recently announced, so there might be a little bit more time for us to digest it and provide more information on that in the next few months. But sorry, back to you, Tanya, just a quick clarification for everyone.
No, that's great. That's great context. And yeah, I'll disappoint on the detail here because, as Lisa said, still a bit of work to be done in terms of whether there's any change in like a program design or equivalent. But I will say that it's a positive that one of the focus areas under the broader Future Made in Australia Innovation Fund is the production of green iron. And so that's very well aligned with ARENA's low emissions iron and steel portfolio priority. And so I think the general view is that this is kind of added momentum to really progress the work in this space and sits neatly with what we're already trying to do.
Yeah, thank you for that, Tanya. I see there's one question for Nicole as well, which is quite specific. I'm not sure if you can see that, Nicole. It's about the price of hydrogen that was assumed to be $7 per kilo. This person is saying for green HBI to be cost competitive with pig iron, green hydrogen must be around $4 per kilo. So, taking into account the new tax credit compensating $2 per kilo, green HBI production is much closer to viability. So can you comment on that if you're able to?
Sure. I mean, my comment would be a general comment. When we did this piece of work, it was close to 18 months ago that we finalised the piece of work. There's been a lot of work to be able to try and bring down the cost of hydrogen production, things like the new tax credit, certainly as the person asking the question indicated, does make it green HBI production much more closer to being viable. There's some work happening in Western Australia around, there's Pilbara Hydrogen Hub that's under development. There's work certainly in the Midwest region, as well as a number of proponents down in and around Kwinana. I've not seen any of the recent price points for a hydrogen production in Western Australia, but with the level of activity that's happening, it certainly sends a clear signal that there's that opportunity, whether the price point is coming down significantly to make it be directly cost comparable. I'm not 100% sure.
I can see someone maybe from BlueScope wanting to jump in.
Yeah, so thanks for the comments, Nicole. I guess, again, this analysis is a bit out of date, but we really thought that hydrogen would have to be less than $2 a kilogram to make it competitive. And that was probably 18 months ago. So, yeah.
Thanks for that. I might just want to go back to maybe BlueScope and Calix with a question around kind of innovative technologies. There was one question around how do you see, and obviously Nicole, if you want to jump in, you're welcome to. But how do you see the potential of direct electrolysis of iron ore? Anyone has any thoughts on that?
It's really interesting. It's very lab scale. I guess the one I'm aware of is Boston Metals in the US. There's other similar processes being developed, but yeah, very, very lab scale. We're talking grams, kilograms at this stage at best. But yeah, interesting.
Yeah, I'd maybe also comment that I think for those of us involved in this sort of work, developing technologies, it's all interesting and we all want it to succeed. So, I think we've just got to be open-minded, and we've got new generations of people coming through that can challenge these technologies more, and we've got to be open to that within the industry.
Yep. Obviously, we can always. Oh, sorry. Back to you, Nicole.
Okay. My observation was going to be that I think what we need to look at is and understand, and from what I'm aware of the BlueScope Steelwork and what Calix are doing, is very much about trying to understand what we can get on and start doing today. There is stuff that we can start doing today. Some of that is deployment of existing technologies just to reduce emissions in the mining of the iron ore in the first instance. Other of it is actually demonstrating existing technologies, but utilising natural gas or increasing blending of hydrogen. And I think that I think where there's opportunity for Australia is not just to sit and wait until the technology is proven before we start to deploy those technologies, but is to actually look at what can we get on and do. That's some of that use of natural gas today. It's that transition pathway, while those other technologies, like the one that you've just indicated, actually do start getting developed and scaled up. And it might well be that will have niche applications, but given that 70% of the globe's steel is made through the blast furnace, basic oxygen furnace pathway, that's got to be a focus of the steel industry globally, to be able to find an alternative solution to that.
Thanks, Nicole, for that additional comment. I guess we're quite close to the end. I might give everyone the very last opportunity to come off mute if you want for the last question. Otherwise, we might move on to the wrap up. Okay, so Anthony, if you can go to the next slide, which is really, really important, please. First of all, I would like to thank all the speakers really for the time today and for the time for preparing the presentation. Really much appreciated. I think everyone really valued your insights, so thanks for that. And thank you for everyone who took the time to join the webinar today. So as we mentioned earlier, if you want to have more insights from ARENA funded project, including obviously BlueScope and Calix, you can go to our knowledge bank, where we will post the recording of today's webinar and also the presentation. And as I said, I hope this event was valuable for most of you, at least, but we are really always keen to improve, and we would love to hear your suggestions in terms of how we can improve in future. So noting that we still have a few minutes before 4 p.m., I would like to invite all of you to really scan the QR code with your phone camera, or open the link that Thomas put in the Q&A to fill up a very quick survey. I promise, it's really quick. So you will also receive a link to the survey in your inbox shortly, so in case you need to run now. But from experience, it's better to get these things done while the event is still nice and fresh in your mind. So please jump in if you can. I'll still be online a couple of minutes in case someone has any issues with accessing the survey or any kind of last question. I'm not going to answer any technical question on behalf of BlueScope and Calix, but happy to take questions from a logistic perspective. Other than that, thanks again, everyone, and have a lovely afternoon.